So, welcome to week 3 of Introduction to Data Science. Now, thanks to all those who joined the competition in GitHub. You all know that there was a competition, so people who joined the competition will receive extra points during the exam. Good morning. So, I hope that everyone knows that there is the website of the book, and this was the competition. The competition was to read a particular file and then to do some operation. Okay. No, it is the attendance is normal. Okay, so tell me, do you all know that there was a competition? If not, however, you make sure that you look at this website, because if you look at this website, you will see the notices and then you'll be able to get extra points before the exam. So those who participate to the activities for sure will have extra points and therefore will come out with the highest possible mark. Those who do not care anything will have the opposite. And during the exam, you will write your GitHub nickname so that I can see what you have been doing, right? Okay, and also thank you to all those who reported typos. I didn't answer the last two notices, but so you can report anything. For example, this was education, there was an A which was missing. Right, so I put it in the so-called this Latin errata corrige, I mean the corrigenda of the book. Right, so you can report anything. Okay, the solution of the exercises in the book is inside the website of the book. Here you can have all the solutions, and I've seen that this guy here has reported something about an exercise. I will keep care of it this afternoon. Despite I'm working hard from morning to evening, sometimes I cannot catch up with everything. But during the weekend, I will do. Okay. Good morning.
So we'll also get the points.
Yes.
We'll also get the points.
Right. Did you send the? Did you?
Notice, but I will look.
Right. Because as I said last time, if you want to be notified, you go to the website and then say, I want to be notified of all activity. And so you receive a message. I mean, okay, if a person tells you something, then if you want to be notified, that was the purpose. Those who were listening to what I was telling. That's because I have to distinguish, I have to discriminate those who participate and those who do not care. So with those who participate, I will do all that I can, possibly can, in order to let them go through. This is, I mean, at least I have to discriminate in some way. And this is a fair thing. Now, good morning. Thursday, October the 16th, there will be a seminar by Professor Aldo Corbellini. And the seminar is about the advanced use of GitHub. Because if you keep working in data science, you'll massively use GitHub in the future. Okay, now it has become the standard. So there is this repo that has been created, GitHub Playground. So here you will be able to, if you want, given that this is, let us say, a playground repo, I will, in the issues, I will ask those who want to participate. Those who want to participate will be invited to participate. Therefore, those who participate will be able to push the files in this repo, right? Because so far, you just have reading access to the repos, for example, the repo of the book. In the repo of the book, you cannot push the file. You cannot, modify our files. But now, here, this is a working thing, so even if a person makes mistakes, but we can always go back. So even if a person tries to delete things, we can go back to the previous state, because here there is a version control of the files. So every operation is tagged, every operation is traced. You do something, you are recorded. You do A, you are recorded, right? And then, just to give you an idea, because when we develop our software, we are all inside this GitHub world. And let me see the branch manager. So you see, sometimes, as you see, these are the releases of FSTA, and then what has been done by which person, and then sometimes it happens that 2 or 3 persons work at the same time on the same files. So you see, these are persons. This was a conflict with a particular release of the software, because some persons were working on the same files. And so now they, up to this, then they've been merged together, their contribution. You can imagine Microsoft, or you can imagine Google. There are 10,000 people working on the same files. Or you have a system like that, or otherwise you do not survive. Of course, because if you work in a software house, but you'll be dealing with it from morning to evening, so you have to know what is, let us say, the state of the art of writing software. And then here you can see the files, everything, who has done what. You see, and then all the releases. So here you keep track of every possible action. Now, so therefore, there will be an issue. Those who want to participate will write the GitHub nickname, because you'll be invited by using your GitHub nickname. Now, last time we talked about algebra and vector spaces. Vector space, a set of objects, these vectors, that has particular operations that you can add vectors, you can multiply them, and the addition of 2 vectors is vector. Then there is the multiplication, which is the so-called inner product, and then the output is still a vector. So the result is still in the set, in a very loose definition. And in this vector space, it is important the idea of base. Base is a set of linear independent vectors. And so each vector of the base cannot be obtained as a linear combination of the others. So all the vectors are orthogonal. Orthogonal means that their degree is 90 degrees. Orthogonal means that the scalar product of their columns is 0. This base defines a set of coordinates, a set of axes, and then we are used to work with what we call the canonical base. That is this vector here. This is the first coordinate where you have 1 and then all the 0. Then the second coordinate has a 1 in second position, and the nth coordinate which has a 1 in the nth position. They defined a set of axes in the n-dimensional space, and these axes are orthogonal. So, for example, in R square, so these are the two vectors which form the basis. Therefore, from here you can choose x1 and x2, and then you can obtain any vector in two dimensions as a linear combination of these two basis vectors, which are our axes, 0, 1, and then 1, 0. You know, the x and y, the y-axis is a basis in R2, clearly, right? Then any other vector can be obtained as a linear combination of them. So, therefore, it is important to understand that if you have a vector, let us say, vector 5, 1, in terms of the original basis, E1 and E2, in terms of the original basis, you see, this one, 5, 1. So 5 for this coordinate and 1 for the second coordinate. Okay, this is 1.7, which is here in terms of the coordinate of E1, and then 3.5, the coordinate on the second vector. So any vector here can be obtained as a linear combination. Now, but why do we have to choose E1 and E2? Sometimes it makes sense to use another reference system, which is given by this V1 and V2, which is another reference system, is another basis, because V1 and V2 are orthogonal, as E1 and E2 are. So exactly the same thing, because we are used to a vector 3, 4, so the vector has coordinate 3 in the first dimension and 4 in the second dimension. But however, you can imagine another set of coordinates, V1 and V2. So if you have this set of coordinates, V1 and V2, these coordinates, 5, 1, how do they transform in the other coordinates? So you have top left, point in the canonical basis. Top right, new axes and coordinates. And bottom point where you do the rotation. Now your new axes become V1 and V2, which are really orthogonal. Still orthogonal. And this is called the change of basis. And why do we do it? Because let me see. You see, this is a trivariate data set, and you can see this plane. And you learn how to draw this plane in 3 dimensions, and you see that there is the first coordinate, the second, and the third. But you can see that the spread of the points is along this plane, not along this plane. You see, this is the best fitting plane, the plane which passes through the directions of largest variability. And here, if you have this plane, it is clear that this three-dimensional data set becomes a two-dimensional and can be explained and can be summarized just by 2 dimensions. So 3 dimensions are not necessary. The points fit very well in a 2-dimensional plane. So you must find the directions of largest variability. So you must pass from this reference system, which is the canonical, which is the standard one, to another reference system. A new basis, so a new set of orthogonal vectors, because they are still orthogonal. This is a plane orthogonal vectors, which describes the variability of your data. And then we want to find the ellipsoid. The ellipsoid in this new 3-dimensional system. And look now at this 3-dimensional system. First, second, and third. You can see that the third dimension is very, very small. You have found a plane that passes throughout your points. You see, this is fascinating, because you have this cloud, now in 3 dimensions, you can see it, but you also want to do it in p general dimension. And p dimension greater than 3, just God can see what is beyond the third dimension. But in principle, that's the idea, that your reference system has to change. And each reference system is given by a set of orthogonal vectors. We are used to these orthogonal vectors, but you can have any other set of orthogonal vectors, provided they all are at right angles, provided they form a basis. So here we have to find, so in general, this in the new basis, which is formed by this new set of orthogonal vectors v1 and vn, then you can have any vector. Can be expressed as a linear combination of these v1 and vn. v1 and vn, we are used to work with this canonical base. But this v1 and vn can be everything. Why not to use the direction of largest variability, for example? And that is the basic concept of multivariate statistics. So this change of basis from the linear algebra point of view is just the multiplication for an orthogonal matrix. You know what is an orthogonal matrix? An orthogonal matrix is a matrix whose columns have a scalar product which is equal to 0. An orthogonal matrix is a matrix such that the transpose is equal to the inverse. It's amazing, this thing, If you want to compute the inverse of this matrix, it is just enough that you do the transpose. Let us see it. Let us see it. Okay. Let me start with my layout. Clear all, close all. Okay, now generate an orthogonal matrix of size. Which size do we put? 5. Okay. Now we use this code, and so we have this orthogonal matrix. So there is, yes, here he uses the MATLAB function ort, okay, orthogonal matrix. Let us call it V. Let us call it V, this matrix. And then this becomes TMP, just a file, a working file. Okay, easy. Here I have the which format would you like to see the result? Format, the default V is with 4 decimal points. People in economics wants to see things just with 2 decimal points, however. Okay, this V. Now, let us do V2 scalar product of V2 and V3, the second and the third column, is what? No. Here I'm taking the second column of this matrix and I'm taking the transpose. So it becomes a row vector. And I'm multiplying by a...
So basically 0, 5 and 0, 4.
Right, and the result of this is what?
So it will be multiplied with 0, 1, 5, 0, 1, 0, 4, and 0, 1, 5, 1, 1.
It multiplies 0.5199 times 0. Yes, and the result of this is what? Or the result of all this, if the matrix is orthogonal, is 0. Yes, it is 0. Certainly. Because the columns are orthogonal. Because the vectors are independent. Now, if you multiply V2 times V5, is what? Still 0. Okay, 10 to the minus 16, 17, or whatever. Now, and if you do this, you get 1. You get what? So you are computing the square norm, if you want. You are computing the sum of squares, the square norm. If the matrix is orthogonal, is 1. So, an orthogonal matrix has all the columns have norm is equal to 1. And all the columns are orthogonal. This defines a new set of axes, a new basis, a new set of axes. Okay? Because we are used to these axes here. And this matrix is orthogonal. You can see, multiply the second column, the inner product of the second and the third is 0. The inner product of the second and the fifth is 0. Right? But why not to use V? Why not to represent the data using this coordinate instead of the coordinate of the identity matrix? Nothing. We still have another set of coordinate system. Now, V times V prime is what? No, V is as size 5 times 5. V prime is size 5 times 5. So you multiply 5 times 5 by a times 5, 5 times 5. And the result is what? 5 times 5. And so what is the result of this multiplication? This is an orthogonal matrix which has, no, is the identity matrix. Because here the inverse is equal to the transpose. It is incredible. Here, for these matrices, to compute the inverse, you just transpose the elements. Because it's just a rotation. This, if you want, all these are just sine and cosine, if you want. And so it's something amazing. With this orthogonal matrix, the columns are 90 degrees, then the matrix is such that the transpose is equal to the inverse. And V prime times V? Same thing. Right. So this V defines really, okay, you see that explanation. Then you see that this is the orthogonal basis. Compute an orthogonal basis for the column space of A. An orthogonal basis. Now you can understand what it says. Is a new set of reference system whose columns are.
Excuse me, I didn't get why if you use the same input, with single port times V.
Right.
Time we get a different output as the identity.
Right, but in fact, I'm not saying that you have to do V square. I'm saying that you have to do V times V prime. V square is a different operation. You are multiplying V times V, and V times V is a different thing.
So it's not commutative.
But matrix multiplication, but, well, let us say, matrix multiplication, apart from special cases, is never commutative, in the sense that A times B is different from B times A. Okay, in general. Not only, but A times B sometimes has even a different dimension that B times A. Okay? Not only that, but the output has a different dimension. Here I'm saying that the transpose is equal to the inverse. Therefore, if the transpose is equal to the inverse, I'm saying that instead of doing V times inverse of V, which is the same thing, here it computes the inverse, here it is enough to do V times V prime, or V prime times V. Okay, which is different from this, which is different from V square, which is different from V times V. Right. Then you can do V times V, V to the fourth, or whatever. Then you multiply V times V times V times V, and this is V to the fourth. Okay. This is matrix multiplication. Okay. And then, which is also different from this. And then if you do this, you do what? Each number is raised to the square. Jolly good. Yes, you see the difference. Here I'm raising each number. Okay, each number here is raised to the square, which is another different operation. Right. There are special matrices. Now that, because if you bring me, I'm very happy. Actually, because these are all the things that I've studied for all my life, not the things about MATLAB. Yes, so I'm very happy about this discussion. However, there are matrices that if you multiply a matrix by itself, does not change. These matrices, I don't know if you have already heard them, are called idempotent matrices. Now, generate an idempotent matrix. Generate an idempotent matrix of size 5. Yes. I mean, if you have had already a course in basic regression, you have probably seen these projection matrix and these P. However, let us let me see. Okay, so these can be removed and P. And what is amazing is that the artificial intelligence already has guessed what I wanted to do. Here, I wanted to show that P times P is equal to P, and there is no difference. Right, so P times P times P times P, it remains P. So there is this matrix here. Okay, P matrix. If I do P times P minus P, and you see it is a matrix of zeros. P squared times P, you see 10 to the minus 13. Don't be cheated, because these are very, very small numbers. These are not times 10 to the minus 13. So the matrix is idempotent. So the idempotent matrix is a so-called, in fact, is for the projection, once again, in regression is very much used. And the idempotent matrix is the generalization of the two numbers which are idempotent. Which are the two numbers which are idempotent? Tell me? No, but if you have, I mean, in dimension 1, what are the two numbers which are idempotent? Which are the two numbers which are multiplied by themselves, they remain, yeah, right. 1 and 0, right, exactly. This is the multivariate generalization, because 0 and 1 are the two numbers that are idempotent. All the other numbers, if they multiply 1.1 by times 1.1, you don't get 1.1. These are the two numbers. Okay. All these matrices can be generated easily using this gallery. You see, test matrices. Gallery. And then here there are a set of, let us say, matrices that are well known in the linear algebra. Some 50 matrices that are very, very important in linear algebra. And the Cauchy matrix, the circulant matrix, let me see, orthog of size, orthog 5, yes. So this is a matrix which is orthogonal. Create this x times x minus x. No. This matrix orthogonal 5, no, this is not orthogonal. Gallery, let me see the help. Gallery. So for example, gallery matrix name, and then you have all these matrices and what they do. Let us see the help for orthog. Orthog returns K type of matrix of order n, where K returns exactly orthogonal matrices. Okay, so K is equal to 3, for example, this should be orthogonal. Orthogonal matrix, not as important yet, of course. Orthogonal matrix in the sense that, of course, its columns are orthogonal. Yes, I don't know why I was here. Right, orthogonal matrix, of course. Now, given that the matrix is orthogonal, can you understand that x is equal to x times v prime? Can you understand that v times v prime, if v is orthogonal, is the identity? So you can write it. Can you see it? If the matrix v is orthogonal, v times v prime is the identity. So here, this gives you this new set of reference system. It's incredible. Therefore, this matrix multiplication gives you the new set of orthogonal system. Now, expressed in the basis determined by V. Now, how is V chosen? That's the thing. Now, this has to do, the choice of V has to do with, and to choose V that such a way that you have a new set of, a new reference system which passes through the points. You have to choose V using the eigenvectors. And now we see this word about eigenvalues and eigenvectors. So you have seen that if x is a vector and A is a matrix, A times x is something which is very complex because you multiply each row by the vector. On the other hand, lambda x, if x is a vector, if lambda is equal to 2, what you simply do to this vector? You stretch it, but the direction does not change. So you multiply the coordinates by lambda. So you inflate or deflate your vector, nothing more than that. On the other hand, if you do matrix multiplication, you transform this vector into another vector. Now, let us now see. It is, if you do the pool, you can have this eigshow, and here it is in this folder. Let me go to this folder. Eigshow. Is inside. No, in fact, I didn't change the folder. No, I did not change the folder. Now I'm going to change the folder. Right? And here there is eigshow. Right. Eigshow. Okay. So you have a vector x. Vector x, which are the coordinates of vector x? 1, 0, not 0, 1, 0, because the first is, okay, the first is the horizontal and the second is the vertical by convention. Okay, now you see this is matrix A. You multiply x by this matrix A, and then you get this new vector, right? If you do this multiplication, you'll be able to see it. Now let us see. If you multiply by this matrix, 1, 0, 0, 1. You can do it. 1, 0, 0, 1. Forgive me those who listen to us on YouTube. At least you have you have not 100%. You have 99.99%. So if you do this, the matrix. And what is the result? Right. 1 times 1, 0 times 0, 1, 0 times 1, 1 times 0, 0. Okay. You see that A times X is this. X and A times X are exactly the same thing in this case. Let us try a different one. Okay. Now, if A now is 0, 1, and then 1, 0, okay, what do you have? 0, here you have 0, and then you have 1, right. So you see that you have done this 90-degree transformation. You see that here, this is the matrix multiplication, and then you can do anything you like. This is the transformation that you do, this is another transformation, and so on and so forth. Or, okay, now, let me, okay, now, let us see. Now, here it says, make AX parallel to X. Make AX parallel to X. Here. Or, for example, here. Well, no, let us see, here. So here you choose, you see A times X in such a way that A times X or lambda times X, just you stretch your vector, is exactly the same thing. Because lambda times X is exactly, lambda times X, if you have 0, 1, you multiply by lambda, and then lambda is equal to 3, it becomes 0, 3. If lambda is 10, it's 0, 10, but the direction does not change. Or if lambda is smaller than 1, you reduce its length, the norm. Right. And then you want to do in such a way that A times X, A is a full matrix, and then in n dimension is an n times n matrix. And you want to do in such a way that this n times n multiplication of this matrix, A times X, is simply stretching the vector, is simply a scalar, a multiplication by a scalar. The first time that I saw it, I thought, but this is impossible. I mean, if you do this matrix multiplication, you have each row times each column, you see, and then you do the sum. How is it possible that a single number, lambda, is equivalent to this matrix multiplication which has n square elements? This is something that has always amazed me. So I say, so this number must be something which is incredible, the magic number. And in fact, these numbers are the numbers which rule the trajectories of the planets in our universe. And it is something which is amazing. So we live in a universe which is mathematical. Something incredible. So you see, these planets that we are in the heart, that all the planets, they circle around with a trajectory which is based on the laws of eigenvalues and eigenvectors. Incredible. Incredible how mathematical the universe is. Now, let us go to this So you see, here what you do, here you have seen that you change your x, and then if you circle around, x provides a circle. Let us rerun it. X provides a circle. See. On the other hand, a times x becomes larger or smaller, and then depending on x, a times x changes. Right. Now, you have to find the two directions for which a times x is equal to lambda times x. When they are aligned there, you see, and then they will be there, they are aligned, right? But also they are aligned here. Where it is amazing because they are aligned when you have the major and minor axis of the ellipse. That's the reason why I was talking about the planets, because the planets have an orbit which is elliptical. Okay, and then the length of the major axis in the three-dimensional space is determined by the eigenvalues. Something which is fascinating and incredible. Incredible. Now, so I invite you, first of all, therefore, to play with these matrices. And sometimes, here you can, but there are matrices in which the alignment is not possible. So, let's see this one. You see, look at this one. Here you rotate x, but it is impossible that they are aligned. And in this case, the eigenvectors are not real, the eigenvalues. And the eigenvalues will be in the complex space. But that's the only one possibility. The eigenvalues always exist, but they are in the complex space. And then, if you have a matrix which is order 2, has 2 eigenvalues. A matrix which is of order 5 has 5 eigenvalues. A matrix which is of order 20 has 20 eigenvalues. Right, and these eigenvalues can be complex or non-complex. How the eigenvalues are computed? Therefore, the first 10 or 15 minutes just to make you feel that you are going to see something that is of paramount importance. This thing about eigenvalues and eigenvector. Because if you understand the thing about eigenvalues of eigenvector, you have a different step. And then you see this, also Google is based, or if you want, is based on, the search engine of Google is based on eigenvalues and eigenvectors. Maybe you don't know, but they always take part in our life. Now, okay, let us keep in mind that if you have this equation, if you multiply both sides by c, you get the same answer. Therefore, in some way, you have to normalize x. And the constraint is that your vector has unit norm. Can you see? Otherwise, there are an infinite number of solutions. Right. So the convention, the international convention is that every time that we talk about an eigenvector, about this x here, the vector that satisfies this equation, this eigenvector has norm equal to 1. Euclidean norm, right, not the other norms. That is the sum of squares, as the square root of the sum of squares is equal to 1. Now, now I want to tell you that if x is an eigenvector of A associated with the eigenvalue, then minus x is also an eigenvector. Well, you see, this is also true for minus x. You multiply by minus 1, So if x is an eigenvector, then minus x is also an eigenvector. In practical terms, what this implies? It implies that, here I've taken those that you cannot align. Okay, this is an eigenvector, and minus x is what? Minus x is this one, where you change the sign, you see it. From x you go to minus x. So the positive coordinate become negative. But the same thing, they are still aligned. Therefore, the eigenvector gives you the direction. Positive or negative does not matter. Therefore, you can find, for example, in where you have a set of variables referred to the quality of life, you can have the ranking of the units in terms of wealth or in terms of poverty. Right. This is what you can do, because the ranking is, you multiply by minus 1, so you can rank the units from the richest to the poorest, or from the poorest to the richest. And you see, everything has the algebraic interpretation. Now, how do you, the eigenvectors of any symmetric matrix are orthogonal. Therefore, indeed they form a basis, a new reference system, right? This is something that we have already seen. Now, how do we find them? Let us follow the algebra. So, A times x is equal to lambda times x. Do you agree about this equation? Tell me. Tell me if you agree. Because the identity matrix is identity times x is equal to x. Okay? Pre-multiplying or post-multiplying by the identity matrix is the same thing. Therefore, I times x or x is the same thing. Right. But A is n times n. And here I have to write the identity, otherwise it is A minus a scalar. Scalar times the identity. So this is n times n minus n times n. Okay. This is a system of linear equation. System of linear, as we have seen the last time. A times x is equal to b. System of linear equation, which is homogeneous. What homogeneous means? Means it doesn't have here on the right side, it doesn't have numbers which are different from 0. So this is homogeneous system of equations. Now, it is clear that you have this system of equation. This system of equation has a trivial solution. And what is the trivial solution of this system of equation? What is the trivial solution? You multiply a matrix by a vector x, which is all equal to 0, and then A times x, which is 0, gives 0. Right. Therefore, what is the only one possibility such that a linear system has more than one solution, an infinite number of solutions? When does it take place? When you have an infinite number of solutions. When the rank of the matrix is not full rank, where the determinant is 0. Right? So, if you have the linear system x plus y is equal to 10, or if you have 2x plus 2y is equal to 20, Same thing. The second equation is a linear combination of the first. Here, the determinant here is what? The determinant of the matrix is what? The determinant is 0. If you want 1 times 2 minus 2 times 1 is the determinant is 0. Right. And so it has an infinite number of solutions. And then in fact you can have 4 times 6, 5 times 5, 7, an infinite number of solutions. Therefore, in order to avoid the trivial solution, which is x is equal to 0, you must impose that the determinant of this matrix is 0. So, therefore, the lambdas are the numbers such a way the determinant is equal to 0. Did you get this concept? So the determinant must be 0. So your lambda must be in such a way that the determinant of A minus lambda I are equal to 0. Well, okay, A minus lambda I. Do you agree that you have this thing? Minus lambda I. Lambda multiplies the elements on the diagonal, So you subtract lambda just to this and to this, because it's lambda times the identity. So the determinant here must be equal to 0. So you have a quadratic equation in 2 dimensions. In 3 dimensions you have a cubic equation. In 4 dimensions you have a polynomial of degree 4. In n dimension you have a polynomial of degree n. Okay. And then this thing here is called universally all over the world characteristic polynomial. Characteristic polynomial. And therefore the solutions of this quadratic equation, in this case you can easily find the solution of this quadratic equation, or otherwise you do it with roots, then the solution of this quadratic equation are 4 and 1. How do you compute these 4 and 1 in MATLAB? With Eig. And then, but every software has got, let us see, A. A is equal to 2, 1, 3. 2, 2. Let me see. 2, 2, 1, 3. Okay. Eig of A. And it gives me 1, 4. Right? Or otherwise you can do, if you want, poly of A and gives you the characteristic polynomial 1 minus 5 and 4, 1 minus 5 and 4, you see 1 minus 5, 4, the coefficient of the second degree polynomial, right? And then here the roots of this second order degree polynomial are 4 and 1, right? 1 and 4, if you want to order from the lowest to the largest, from the largest to the lowest, whatever, okay? So you don't need to compute poly and then roots, because Eig does the job. Then, not only you want to find the eigenvalues, but you want to find the corresponding eigenvectors, because they are a pair. To each eigenvalue, it corresponds an eigenvector, right? So how do you find both the eigenvalues and the eigenvectors, you find them with eig called with two output arguments. So eig A gives you the eigenvalues. Now eigs A called with two output arguments, for example V and D. Disp V and disp D. Show eigenvectors, and show matrix of eigenvalues. Okay, let me run it. Okay, let me do this. Okay, right. These are the eigenvectors, first and second eigenvectors, and these are the eigenvalues. The eigenvalues, the n is missing, we don't care. The eigenvalues are put in a diagonal matrix. Right. Now, but these two numbers, these eigenvalues, 1, 4, must be a sort of magic numbers of the matrix. And then here you can see that the sum of the two eigenvalues is equal to the trace of the original matrix. So you see, 1 times 4, 1 plus 4, is equal to the sum of 2 times 3. The sum of eigenvalues is always equal to the sum of the elements of the diagonal, of the original diagonal matrix. Not only, the product of the eigenvalues is equal to the determinant of the original matrix. And then we are going to see it later on. Well, what is the determinant of A? Tell me. 4, of course. And now, what is the product of the two eigenvalues? 4 times 1 is 4. It's exactly the same thing. So they must be magic numbers in some way. Now, let us see. Let us keep going. Okay. There is a theorem in linear algebra, and then we are going to use this theorem, that says that any real symmetric n times n matrix admits the decomposition in terms of eigenvalues and eigenvectors. And now we do it. Note that matrix V is such a way that V is orthogonal. You see that V prime, V transpose V is equal to the identity. So these V1, Vn form an orthogonal basis, of course, in Rn or complex numbers, space of complex numbers. Okay, now we try to do it, because I want to make sure that you have understood, and I want to make sure that you understand this equation. So we say that this S can be written as matrix of eigenvectors, matrix of eigenvalues. When I mean matrix of eigenvalues, I mean the matrix which has the eigenvalues on the main diagonal. Matrix of eigenvectors times the matrix of eigenvalues times the matrix of eigenvectors transpose, okay, you get the original matrix. And remember, what is the meaning of V? Is a new basis, a new basis vector. Now, let us, okay, now look at this equation. Do you agree that V is V1, V2, and Vn? Now do the multiplication. You see this V1 times lambda 1, and all the other are 0. Then we have V2 times lambda 2 times lambda n times Vn. You get it. Why you get this 1 times n vector, which is the multiplication of this by this? Can you get it? So is V1 times lambda 1, then is V2 times 0, plus V3 times 0, plus Vn times 0. So you end up with lambda 1 V1. And then you do this multiplication here. So you agree that you end up with this, eh? Okay, now, and this is the code. Reconstruct S as a sum of rank 1 matrix. Shall we do this code? You want to see me do it or not? Because I don't know what people. We do it. Okay. Okay. Now, you want to have an MLX file or an M file? M file, not an MLX. Okay. Okay, now, generate a symmetric matrix, which is also positive definite, and the last time we see what it was. So x is equal to randen 10. Which dimension would you like to have? Okay, we put it p. We put it n and p, so that we will be very flexible. So n is equal to 100 and p is equal to 10. Then we change p and then all. Yes, right. So, and then we generate this matrix X, which is the covariance matrix of this X. In order to be able to replicate the result, we put the seed of random number to 100. Now, everyone should have this initial matrix. Matrix is symmetric, fine. This is the covariance matrix, and now okay, compute the eigenvalues and eigenvectors. Okay. So, therefore, this is matrix V, this is matrix capital lambda. If you want, we have done this. We have found this V and capital lambda. Right? Oh, you want to call it maybe capital lambda? Let's call it capital lambda. Lambda. Okay, TMP, okay, because there is another TMP maybe, eh? Okay, well, let us change folder. TMP, okay, very well. Now, V times lambda times v prime, which is S reconstructed, okay. That there was also the artificial intelligence that had already given me the code as reconstructed. Okay, this is as reconstructed. Now, S reconstructed is the multiplication of these three matrices and S. So the difference S minus S reconstructed, let me see, abs of this is the absolute value of the difference between these two elements, and maximum of the difference, and of all elements is smaller than 1 to the minus 10. Max diff. Let me see, the max, the absolute of the difference, and then the maximum. The maximum of this is what? Is 10 to the, let us put in such a way that, look, it is smaller than 10 to the minus 10, mass diff. Okay. Okay, you see that now the artificial intelligence that already has guessed what I want to show. This is the code that he has written. If max diff is is true, is equal to true, or therefore it is equal to true, well, it is much better to specify equal true. So if max diff is equal to true, the reconstruction is accurate. Otherwise, the reconstruction has discrepancies. The reconstruction is accurate. Right. So we have been able. Now, let us check that V is orthogonal. V primes V, identity matrix. Right. V times V prime, identity matrix. Right. And then this is really an orthogonal matrix. Now, let us see now this thing here that we want to do. The first column of V times lambda 1 times V1 transpose plus, you see this sum here. Can you see here? Each element of the sum, because this is the sum of n matrices. Each matrix has a size what? N times n. And then you do the sum of these n times n matrices. Here we are in dimension 3. And so, second reconstruction. Reconstruction. Okay. Modify the eigenvector for the second reconstruction. No. I don't want to do it. No, this time the artificial intelligence has done it wrong. Absolutely, I don't want to do it. Okay. So now I have to do first column of x times 0.8045 times the transpose of the first column of V, okay. First column of V times lambda 11 times first column of V transposed, then plus second column of V times lambda 2 2 times V second column of V transpose. So is columns I column times lambda the element II times V I transpose. So for example, if I, for example, is equal to 1, and then, okay, so you see this is a matrix, because this is 3 times 1 times 1 times 1 times 1 times 3. This is a matrix. Okay, now we call it, I don't know, AJ. AJ. The rank of AJ is what? The rank of AJ is 1, is the column, the transpose, each column is a linear combination of the other, right? Is absolutely, the rank is equal to 1, and then I have to do it for I is equal to 1, then I have to do it for I is equal to 2, and then I have to do it for I is equal to 3. Therefore, SCHK so I initialize SCHK, which is equal to a matrix of zeros of size P. Okay, this is initialized. The artificial intelligence is always amazing. Now he has understood that I want to do it the loop. Isn't it amazing? Can you say yes? Amazing. Amazing. It has anticipated what I wanted to do, the loop. The loop from I, which goes from 1 to P. Incredible. Incredible. He has anticipated, well, has followed my logic, and then he has proposed what I will have to say. Incredible. So, you see, now, can you see this code? SCHK is initialized as a matrix of 0. Then, when I is equal to 1, I take first column times the element 1, 1 of lambda times first column transpose, plus the same thing for I is equal to 2, the same thing for I is equal to 3. And this is precisely this implementation, right? But what is amazing is that the artificial intelligence has not seen my slides. So he doesn't know that I have these PowerPoint slides. But on the other hand, he immediately did it. Of course, the artificial intelligence, if you know the algebra, is incredible. Otherwise, if you don't know anything, you have no idea of what is proposing. So you see, S is a linear combination of rank 1 matrices. Now, so, and second reconstruction matrix, yes. Artificial intelligence, okay, fine. And now check, okay, incredible. Verify the accuracy of the second, incredible. But look at what these engineers of MATLAB have done. It's incredible. I don't even know, I can even now talk to the computer. Yeah. Now it says what? If. Right. Okay. Okay, also this thing about the if automatically has come out. Isn't it amazing? Maybe in 3 years' time we will not be amazed anymore, but now I'm still amazed. I'm still amazed. Okay. Now, before we said that the sum of the eigenvalues is equal to the trace of the original matrix. So S is equal to V lambda V prime. So the trace operator is the sum of the elements which are on the main diagonal. For the trace of S is equal to the trace of V lambda V prime. But the trace, despite the matrix multiplication, the trace, if you go to chapter 2, the trace is commutative. So the trace of A times B is equal to the trace of B times A. Therefore, this V lambda V prime can be written as lambda V prime V. But V prime V is equal to the identity. And that is the proof that the sum of the elements of the original matrix, the trace of the original matrix, is equal to the sum of the eigenvalues. Okay? Let us verify it. Trace of S. Okay, TRS. And the trace of lambda. TR al. No, this one I don't want to know the conditional number, I don't want to have it. I wanted the trace of S is 3.04, okay, the sum of these 3 elements on the diagonal. And the trace of L, exactly the same thing. Incredible. Now, the determinant. The determinant of S is equal to V lambda V prime. What is the determinant of an orthogonal matrix? What is the determinant? Is 1 or minus 1. So the determinant of V is 1 or minus 1. The orthogonal matrix have determinant which is equal to 1. Therefore, you have, for the laws of the determinant of the product is the product of the determinants. This is 1, 1, and so this determinant of S is equal to the determinant of lambda. But lambda is a diagonal matrix, and what is the determinant of a diagonal matrix? What is the determinant of a diagonal matrix? No. Of a diagonal matrix. What is the determinant, for example, of this matrix 3, 0, 0, 4? What is the determinant of this matrix? Exactly. The determinant of the diagonal matrix is the product of the elements on the main diagonal. Is the product of the elements of the main in the main diagonal, right? Therefore, the determinant of the original matrix is equal to the product of the eigenvalues. It's amazing, eh? And then you can prove it in the 2 or 3 lines. Let us see it. So, the diagonal of lambda you take the diagonal elements. Okay? And then you take the product of the diagonal elements. Okay? This is the product of the diagonal elements. And then you say, what is the determinant of the original matrix? Exactly the same thing. But don't you think that these numbers that rule the orbits of the planet have something to do with magics? That's incredible, eh? But what is the determinant? The determinant is the volume of the ellipsoid which encloses all the points. Incredible, eh? This is the meaning of the determinant. Therefore, the meaning of the determinant, what are the eigenvalues and the square root of the eigenvalues? The square root of the eigenvalues are the major semi-axis of the ellipse or of the ellipsoid. So if you do the product of the major axis, semi-major axis of the ellipsoid, you find the volume, which is the determinant. Incredible, eh? So you see this orbit of these planets, you imagine they have a volume. And then it's just a product of these numbers here, of the eigenvalues. It's incredible, eh? It's incredible of the universe we are living with. Therefore, but however, the more you know and the more you'd like to know. So now this is another example, and then you can do it with a pen as usual in the original way, without any artificial intelligence. Or you can do it using symbolic computation. In the sense that here, if you define that x is symbolic, and then the integral of x is a square divided by 2, I don't know if you have ever tried this symbolic computation, but I always insist with my colleagues of mathematics that they should show you these things, because all this symbolic computation, for example, seems x, and then you say the integral of x is a square divided by 2. What is the integral of x squared? Is x to the third divided by 3. Right. What is the integral of 1 over x? Tell me. What is the integral of 1 over x? Tell me. Ma no. Is log x. The derivative of log x is 1 over x. Come on. This, in the past, I've studied these things I've studied things for all my life. Let us say that I've always been around these things for all my life. However, these are things that you never forget.
I thought it's extra knowledge.
Ah, okay, so you are forgiven, right? Okay, and then on the other end, the derivative of log x, 1 over x, or the integral in maybe 0.02, right? Or the limit. You can do everything. You see, you can compute any operation: limit, derivative, integrals, any integral. Now, let me say something about when you project a vector. You project x into y. You project x into y. What is the length of the projection? So you see it. Y, this is projected, x is projected into y. So you have to see the length of this projection. Well, the length of this projection, 1, again has to do with the scalar product. Therefore, from the algebraic point of view, if you do the scalar product, dot product, call it whatever you like, then the length of the projection is equal to the inner product. So if you project into a vector y which has a norm equal to 1, so the length is equal to the scalar product because the norm of y is 1. So if you project into this vector which form a basis that are orthogonal, that have norm equal to 1, then the scalar product is just the length of the projection. It's amazing, eh? Then you have, if you have the files and in the book where you have also in 3 dimensions, this third coordinate that you project it, okay, so this is the end of the first part, because that was very important and is an incentive to check carefully chapter 2, which is linear algebra. And then chapter 2 contains many more things that we were didn't have time to say. However, the encouragement is, of course, tomorrow, please tell me everything you do not understand. Not only computationally, but also scientifically, also from the algebraic point of view. Thank you. So we see again at 10:45.